Hey, good afternoon, everyone. My name is Matt Selensky. I'm a computational scientist at NREL, and joining me today is Olivia Hall, another scientist here. And today we're going to talk about how we are using one of the many MLPerf benchmarks as part of our supercomputing project. So with that, I'll turn it over to Olivia for project, and then we'll circle back to me eventually during this talk. Thanks, everyone.
Nice, thanks, Matt. Yeah, next slide, please. Okay, yeah, so before we get into things, we wanted to do some quick introductions. So we are computational scientists in the Advanced Computing Solutions Group at the National Renewable Energy Laboratory, or NREL, which will be called National Lab of the Rockies going forward. This is a Department of Energy, or DOE, national lab. And the primary purpose of our group is to enable computational researchers at NREL and DOE to take full advantage of our supercomputing capabilities that we host here on site. And so there's a ton of different activities that fall under this very broad umbrella of work. But for me, I lead the supercomputing benchmarking efforts at the lab, and kind of relevant for this talk is in leading the development of the benchmarking procurement suite for the next generation supercomputer. So this is putting together a set of benchmarks that will help us make decisions around getting a new supercomputer. And Matt leads the supercomputing technical engagements, and then most relevant for this talk is that he also leads the development of the AI and machine learning component of the benchmarking procurement suite, which we've used MLPerf for, and we'll talk all about why we think that has worked really nicely. So because of the remote format for us, and also thank you very much for the flexibility and being able to host us remote, please reach out to us via email if you have any questions or comments or thoughts or anything like that. We put our emails on this slide, and then we'll show them again at the end. And I know it's less exciting than a live Q&A, but we would love to hear from you if you want to talk more about anything we're presenting here today. Okay, next slide, please. Okay, so this is kind of the big idea of the talk. We want to buy a new supercomputer, and how do we make sure that what we buy suits our needs? And then, how do we use benchmarks to help us make sure it suits our needs? And then more specifically, how can MLPerf help with this process? So next slide, please. Okay, so kind of the big overview for our talk today. So I will do the first half and kind of just talk at a high level supercomputing at NREL. What is a benchmarking procurement suite? How does it help with a procurement and that sort of thing? How I think about choosing benchmarks for the suite, and so on. And then Matt will come in and talk about MLPerf as part of the suite, the MLPerf DeepCam benchmark specifically, and all of the really great work that he's done with this benchmark for the suite. So next slide, please. Okay, so when we want to talk about, getting a supercomputer that meets our needs, one of the first things I think we should think about is just how we use the computer in supercomputing now. So this is a little overview slide about that. We host the primary computing facility for the DOE's Office of Critical Minerals and Energy Innovation, or CMEI. And our current system, our current kind of flagship supercomputer, is named Kestrel. And it's CMEI's third generation supercomputer. It delivers about 44 petaflops of computing and 95 petabytes of storage. And then the heterogeneous architecture. So we have a number of CPU only compute nodes, and then also some GPU accelerated compute nodes. So we have about 624 NVIDIA H100 GPUs, and then about 2,300 CPU only nodes. And kind of how it works is that NREL provides a service to the CMEI community where the primary way Kestrel is used is by research and development projects that fall under various technology offices under CMEI. And then 85% of the compute goes toward those projects and that kind of work. And then 15% of the compute goes toward kind of NREL discretionary usage. So down there at the bottom, I have just a couple of highlights of some of the different domain areas that we support. These are things like integrated energy systems and material science and manufacturing and all sorts of things. And next slide, please. Okay, so this is kind of looking just at growth in computing on NREL supercomputing resources. And then on this left-hand side, this pie chart is showing, this was from fiscal year 2024, the compute usage by technology area. And what I really wanted to highlight about this chart is the huge variety of different domain areas that we support in their research on our supercomputer. So these different domain areas often use different applications, different algorithms that have different, memory access needs and different communication needs, and all sorts of different needs in terms of how we maximize their performance on our system. And then when we look in this middle chart, this is showing the annual requests for computing since fiscal year 2020. And I did chop off the y-axis because the units are confusing and took up too much space. But effectively, it is just the available compute that's being requested. And what we see is a trend where demand for compute is always exceeding availability year over year, and that we are growing in how much compute is available and how much compute people want year over year. And when we look kind of more specifically at AI and machine learning, what we see is that this AI and ML demand has grown rapidly in recent years, and we expect this trend to continue. So when we look at this growth kind of breakdown in terms of AI ML, we see that a lot of the growth is in this area. And something to point out here is that if you look on the pie chart, there is no AI ML slice of the pie, right? It's that all of these different domain areas are starting to leverage more and more AI or machine learning in some way or another. Next slide, please. Okay. So we'll talk now more specifically about developing a benchmarking procurement suite, what that is, how it helps us, and so on, now that we've kind of had a look at, the type of compute that's done on our system. So next slide, please. Okay. So I wanted to start this off by showing a timeline. So how benchmarks are used in our HPC procurement, kind of through the whole life cycle of the procurement. And different institutions will, of course, handle this in different ways, but this is how we've been approaching it for this procurement cycle. So first thing to notice, I think, is just how long this cycle is and just how much mileage we get out of these benchmarks through the years that we plan on using them. So we started the development of this suite in late 2024, and then anticipate that once this new machine goes into production in the spring of 2028, we'll still use these benchmarks as a way at that point to just monitor the health and functionality of the system and make sure everything continues working the way we expect. There's a lot of steps in between too. So in spring 2025, we released a draft benchmark suite kind of officially and publicly so that we could have vendors take a look at what we're thinking and if they had thoughts and feedback to get that from them, because as we'll see, the way that vendors run the benchmarks is a very integral part of this process. And so their feedback is extremely welcome and has been extremely helpful for us. And then kind of the really big one is where it says RFP in bold and red in summer 2026. RFP, I put the little definition off to the right. It stands for Request for Proposals. And essentially responses to the RFP are proposed new supercomputers. So we put out this RFP document that says a lot about what we do with our computing and what we're looking for, and the benchmark suite kind of formally goes out with the RFP, and then the responses are, the vendors say, hey, here's a proposed supercomputer design that we think is going to meet your needs. So part of that RFP response is that vendors will take our benchmark suite and they will run the benchmarks on their current hardware. And then a very fun and interesting complication is that they might not have the hardware that they're proposing for the supercomputer on hand. And so then there's also a step of making projections and predictions for how these benchmarks will perform on hardware that may or may not exist yet as well. And then, so, we make a decision around which proposal to go with. And then the next step would be where it says, or there's a lot of steps, but steps most related to benchmarking. The next one would be acceptance and 2027. And essentially what that is the computer arrives on site and is put together and turned on. And then one of the checks that you do to make sure that the computer is working the way we've all expected is by running these benchmarks again and making sure that their performance and function is kind of in line with what we expected. And then once we go into production, as I mentioned kind of earlier in the slide, we would then run the benchmarks again just to monitor, how the system is doing using a set of benchmarks that we've now spent many years developing a lot of expertise around. So kind of in this first half, pre-RFP, this benchmark set is a way for us to communicate requirements and a way for us to say, kind of through the software and through the design of the suites and the applications we include and that sort of thing, what's really important to us in terms of those softwares. And then after RFP is a way to ensure that all of those requirements are met. So kind of the main takeaway is that these benchmark results are a way to measure improvement from the current machine to the proposed new machine, and also a way to communicate what we are thinking of in terms of improvement, right? Just the benchmarks themselves and how we define them is saying something about the way we're thinking about improvement. Okay, next slide, please. Okay. So when you think about hardware, these are kind of what I think of as like the pillars of a supercomputer. So there's compute and storage and network. And under compute, we have things like the types of CPUs or types of GPUs or accelerators, the memory bandwidth of those things, the flops of the CPUs, the flops of the GPUs, and that sort of thing. Under storage, we'd have things like the read and write bandwidth. We'd have the number of I/O operations per second that you can sustain, the number of metadata operations per second you can sustain, and kind of things like that. And then under network, the classics, bandwidth and message rate and latency. And kind of the key here is that any one of these things could be the bottleneck for your computer. And so you want these pillars to be nicely balanced so that they can support the work that the users and researchers are going to be doing on the computer. And what that balance is can really be totally different institution to institution, just depending on how people are going to use the computer. And so we want to kind of construct a set of benchmarks that will help us get the right, balance of the pillars correct for ourselves. So when we think about the types of benchmarks, I kind of think about them in three big categories. One is something called micro benchmarks. So these stress one thing typically, or just a couple of things. They're simple and controlled. And because of this, you have to be a little bit careful in how you look at them and how you think about them. They can be gameable in certain ways. So for example, we have a micro benchmark that will just try to measure the bandwidth between one compute node and another, so looking at the network bandwidth. And you can kind of imagine that if you only had micro benchmarks that are only looking at each of these components individually or nearly individually, that you might end up with a system that does things well individually, but then maybe when you put them all together, the application performance wouldn't necessarily be quite what you want. So you also want to have applications in the suite that are represent domain areas and kind of, again, capture maybe some of those key algorithms or workflows and patterns that your researchers use. And these are typically not simple. And then the bottleneck can really depend on the hardware. In a micro benchmark, you don't kind of have a bottleneck in the same way, like in our example of the bandwidth test. If bandwidth isn't the bottleneck, then something has gone terribly wrong. But in an application, depending on kind of the balance of these pillars, you could have the bottleneck show up in different ways. And then kind of for completion, there's another category called proxy apps, which we don't actually have any of, so I won't talk too much, but did mention. Next slide, please. Okay, so when we think about benchmark coverage, essentially we want a minimal set of benchmarks that maximizes coverage, not just of these hardware pillars, but also of this kind of extra dimensions I've thrown in here. So this coverage is more than just the hardware. We also want to make sure we are capturing what stakeholders want and that what we're asking for is reasonable for vendors to do. So kind of the more familiar and more, well-known, say, an application is, the easier it's going to be for other people to run versus maybe something that's like totally in-house, right? There's kind of that kind of consideration. And then there's what users are doing now and what users are doing in the future. We care a lot more about what users are doing in the future for a future supercomputer, but what users are doing now is a little bit easier to tell. So we think about that as well. And when we think about AI and machine learning, in general, it's a great area to have a benchmark for because this is an area that stakeholders care a lot about. It's something that we know users do now. It's something that we can, look at that growth trend from a few slides ago and know or be fairly confident it's something that users will do a lot more of in the future. And it's something that's demanding on the hardware and complex, and the bottleneck can be something different kind of depending on the hardware. So Matt will talk a lot more about this again for this benchmark specifically. But yeah, next slide, please. Okay, so before we get into the ML4 benchmark specifically, I just have 2 more slides. This one is on, once you've decided on, you have a set of benchmarks that you want, how do you construct them or define them in a way that you learn the things that you really want to learn? And we do this with something called run requirements. So the run requirements are a set of rules that the benchmark response must follow in the RFP. And kind of the question is, what are we trying to learn and what rules do we need to enforce in order to learn these things? And kind of on one hand, the more flexible the rules, the easier it is to respond, but the harder it is to interpret apples to apples, say, between our old machine and a new machine. On the other hand, the more rigid the rules, the easier it is to accidentally box yourself into interpreting apples that you don't actually care about. So an example of this is in mandating particular software versions. So this might seem like a really kind of mundane choice that you just have to make, but can have some sort of interesting effects. So for example, let's say, on your current system, you run version 1 of a software, and then you put the RFP out and version 2 comes out. And then kind of what happens. So if, during the RFP response, they use version 1, maybe version 2 has changes that can better take advantage of new hardware. And so it's like, well, you're comparing more apples to apples because, there's no changes between the 2 versions. But then when you think about, well, if you let them use a new version that can take advantage of their hardware better, that's going to be something that our users would actually use on a new machine. So do you let them do that, right? Even though those changes would kind of make it so that the apples to apples comparison is a bit harder. So there's a lot of thought that has to go into it and thinking about, when you make a decision with respect to these rules, what kind of the consequences can be, and hopefully they're intended consequences. Next slide, please. Okay, So to kind of wrap up the just benchmarking procurement and what it is and what we're trying to do section, I just wanted to run through kind of the list of goals for a benchmark set overall for this. And so we want a set of benchmarks that, first of all, are broadly representative of workloads at our institution, that stress the components of the HPC system or supercomputer system that are critical bottlenecks for these workloads, that allow us to understand the performance and functionality of new machine, that help ensure functionality down these software tool chains, the dependencies that an application might use. And then these ones in bold are ones I maybe haven't talked quite a bit about as much, but are, I think, things that this the MLPerf can really hit on very nicely, which are benchmarks that vendors are familiar with and that are open source and reproducible, and kind of maybe most important of all, trusted by research communities. So next slide, please. And with that, I will hand it over to Matt.
Awesome, thanks, Olivia. Yeah, and so from here, I'll sort of walk everyone through how we came to the decision of choosing an AI benchmark, including settling in on MLPerf, narrowing in on DeepCam, which is the specific model that we're using for this procurement project, and then concluding with just a few impressions we have from our experience and some feedback we've gotten from our stakeholders throughout this whole thing. Next slide, please. So how do we decide a particular benchmark? Like Olivia sort of just laid out all of these things we have to consider. How do we actually do that in practice? Well, at least what we did on our team was sort of a three-pronged approach in a general sense. So the first and perhaps the most obvious is we did a lit review, basically. We wanted to see what was done before. One of the benefits of being at a DOE national lab is that there are other national labs out there, and they also buy supercomputers. And we all make our RFPs public as this process goes on, and they're sort of just out there. So great resource for us to consider. Really, any institution trying to procure a machine like this could probably learn a lot from reading those RFPs. In a similar sense, Olivia and I and many of the folks we work with at the lab have a whole slew of contacts at different hardware companies, maybe software storage companies, stuff like that, who we work with in our day-to-day roles, who, we have a good relationship. We can ask them what they tend to see in RFPs and what's difficult or easy for them to accommodate. So kind of keeping that relationship and maintaining those is equally critical. Some other things we do is we are very much about making data-informed decisions on our team. We maintain a very large database of every job that users submit to our HPC system, and we do regularly mine those data to inform decisions around procurement like this, sort of in addition to understanding where we now, how are people using this very expensive slew of hardware that we currently maintain. It's very useful for that. The third thing that we do, sort of similar to the first point here, is just talking to people. We try to make this open as much as possible, pretty much from the start. So we engaged with our scientific stakeholders very early on in this process. We really wanted to understand what directions their research might take in the near future and translate that to required hardware. Because as Olivia said, there's not necessarily like an AI office at NREL who we can just kind of go to and quickly get some answers. We have some people who do AI primarily for their research, pretty much a handful of them at the laboratory. But what is much more common is domain scientists from a whole variety of different fields and backgrounds applying AI to their specific work. So we spent a lot of time talking to a lot of people across that spectrum to get their perspective. Next slide, please. And, that is all well and good, but it is hard to make a good RFP benchmark, I would say, even when you do your homework in the ways that we did. So With respect to hardware vendors in particular, there's sort of this additional layer of technical challenges that we really have to balance. We have user needs and stakeholder needs, but we also have what can we feasibly ask for in this time period. So, I think probably everybody in the auditorium I'm speaking to now would probably agree with this, that there are always going to be some specific caveat, consideration, thing to keep in mind on any given system that you try to deploy an AI model onto, especially if you're doing something fairly complicated like distributed training tasks. There's always something you run into and have to debug that you probably can't anticipate beforehand. That's just sort of HPC in a nutshell. So we got to be aware of that and sort of make the benchmark reflect that fact. We also need to be very much aware of where the benchmark sits right now and in the future. So as Olivia showed earlier in the presentation, we operate on multi-year timescales, but that is sort of diametrically opposed to the speed that the field of AI and machine learning operates at. It's much faster. Things go out of date all the time while we are still sort of slowly catching up and maybe understanding it ourselves. So we need to be aware of that too. Data availability is another big concern. The DeepCam benchmark that I'll talk about in a few slides here is using roughly 9 terabytes of data to train on. And while that is hosted at another public national lab here in the US, getting that data, making vendors aware that they need that data, communicating that and making it available is equally critical to anything about the software that we're actually trying to run as part of this. And so finally, as Olivia alluded to, a lot of this really gets expressed in our benchmark requirements, and we can't be overly prescriptive with how these benchmarks are run, because not only does that make comparing results difficult, you could also, in effect, bias the procurement towards certain vendors, which, as a mostly publicly funded institution, we really don't want to do. We want it to be open and fair. Next slide, please. And so we really see that MLPerf comes into the suite at this moment and is very helpful to address many, if not all, of these concerns. Next slide, please. So as we've heard earlier, MLPerf is a very wonderful framework for deploying all sorts of different benchmarks. There are different suites that are tailored for different use cases or different things that you maybe want to test. And the thing that our institution in particular really cares about and tries to do for scientific purposes is distributed training for various things. So we settled on MLPerf training HPC, which is basically just asking how fast can we train a big model to a target quality metric on a supercomputer. As many of you probably know, this was actually retired in January of 2025. I have a note on this later, but just put a pin in that for now. A big benefit that sort of tuned us into MLPerf from the very start was that the general run rules are established by a community of experts. It spans academia, industry, government. Everyone's on board with this, and everyone contributes to that. And that was a very positive thing to see. And another great thing as well is that there are some actively maintained benchmarks in these suites today. There are many more that are deprecated, but the point is there's a reference for all of them. Even if something isn't actively maintained and it fits your institutional use case to the T, you could theoretically take that, develop it, and make it a benchmark for your institution, sort of forked off of MLPerf a bit. Next slide, please. So I want to talk a little bit about some pros and cons maybe of using MLPerf as a framework for the type of procurement benchmarking that Olivia and I are talking about. So, we've established this is a standardized framework with a lot of community-driven input and feedback, which is great. The benchmark run submissions can also be public. So, we see hyperscalers or maybe a supercomputer integrating integrator companies rather, submitting certain benchmarks to the ML Commons leaderboard. And that is a very useful thing to see from the perspective of people trying to deploy benchmarks for procurement, because in addition to the knowledge you can get about how that benchmark runs on your system with the configuration you understand very intimately well, you can also get a glimpse of how it might perform on other hardware that may or may not be a lot more like the hardware you're trying to buy. So that alone is very much a huge pro to MLPerf. Because vendors contribute to a lot of the benchmarks under the umbrella of MLPerf, many of them are very familiar with the suite. And as Olivia alluded to, that sort of level of comfort for vendors or enabling them to feel like the work that they're being asked to do is feasible kind of helps move that proposal along and hopefully broadens that bidding landscape for us, and we get a better machine as a result. And there's a large variety of benchmarks that target different workloads and system components. So from our perspective, that's great because we have a lot of things we want to test. So it's great to have a lot of options. Next slide, please. I'd be remiss if I didn't try to mention at least some cons. And I just want to mention kind of the main two that have come up for us. And I can hopefully speak a little bit about how we tried to solve these. So the first, and really this is not truly specific to MLPerf, is that, you know, as the person doing the benchmarking, you have less control. So what happens if your chosen benchmark or even the chosen benchmark suite is decommissioned over this rather lengthy time period that we like to do our procurements on here at the lab? That did actually happen to us with DeepCam, but it's okay because of that historical reference of all of the scripts and all of the results over time. It ended up not being too big of a concern for us because we essentially just forked the repo, added a few things here and there, thought hard about our run requirements, and we think we can continue using this without a problem, and vendors seem to think so as well. The other challenge that is sort of maybe an outstanding one is the fact that scientific AI ML, quote unquote, implementations tend to be a little hard to genericize. And especially even in our own institution, you could have one person trying to train some kind of CNN on, you know, some computational fluid dynamics data using some particular flavor of data format, while another researcher is doing something similar. They might be having totally different approaches. The workflows might be totally different. It's hard to make a benchmark for something that flexible. Next slide, please. And one more. Just in the interest of time, I'll kind of breeze through this. So the outcome of a lot of our engagement tasks and analytics that we've done, which, you know, funny to see this condensed into just a couple of bullet points. This is about half a year's worth of work. The outcome was basically that segmentation tasks via PyTorch are broadly used amongst our researchers, and many of them plan to do much more of it going forward. The sort of big takeaway from this is that people aren't using our supercomputer to train massive LLMs. They tend to do more physics-informed AI using things like convolutional neural networks and stuff like that. Next slide, please. So after quite a bit of back and forth and trying a few benchmarks that, you know, maybe didn't work or fit our requirements for one reason or another, we eventually settled on DeepCam. And if you could just hit next one more time of the little animation. This is from the MLPerf training HPC repo, which again was retired in January 2025, but it just so happens that DeepCam hits so many of our institution's requirements, we felt compelled to use it anyway and kind of continue stewarding it in a way, I guess, as part of this procurement. So this model comes from some Gordon Bell winning work performed by people at NERSC, another DOE computing facility, I guess in California. You guys are closer to it than we are. where that model is segmenting CAM5 simulation data, climate simulation data, to identify extreme weather events at the pixel level from these files. This involves training a convolutional neural network on about 9 terabytes or so of that CAM data to a target evaluation accuracy. And this benchmark, if I remember my provenance sort of correctly, was created as part of this paper I linked below. Excellent paper, by the way. I recommend everyone read that if you haven't already. And it won this Gordon Bell Prize, and it turned out it was such a good benchmark. The folks at NERSC kind of worked with the people at MLPerf, and now it's sort of a general benchmark that you can use for different things. Next slide, please. So what does this benchmark actually give us as an institution? Well, first, it captures a popular AI use case at our lab. It ensures a degree of functionality and performance for the tools that drive AI/ML, and I'm thinking of PyTorch specifically on our next system. And it doesn't have to be PyTorch, it could be whatever eventually replaces PyTorch. But the point here is that in addition to the thing we're benchmarking, since this is sort of a complicated workflow with a rather complicated software environment behind it, making sure it's performant is just as important as making sure that that complex software environment can work on this new system right off the bat. So this really increases stakeholder confidence and decreases the risk that we are effectively buying a lemon for AI. No one wants that. It also, on a similar note, it allows us to understand how that proposed hardware would actually perform in a real-world training scenario. Those micro benchmarks that Olivia mentioned before will definitely give you a nice, clean number to look at, but they are not necessarily messy applications in the same sense as running a distributed training AI model is. Many benchmarks are neat, but this one is messy, and I view that as an absolute strength in terms of procuring a supercomputer. We have a lot of training data. We have a ton of knobs that we can turn on various hyperparameters or data loading strategies. Vendors are free to do that in a sense, and I'll get to that in just a second here. But we basically, at the end of this, get a blueprint for how we can performantly run complicated AI/ML workflows on a future system, which for folks like us, Olivia and I are not necessarily experts in AI or driving the development of these tools like many of you are. That is very worthwhile for us and a huge time saver and resource saver for the institution. Next slide, please. And if you could hit it 2 more times, I just got a couple of animations here. So getting back to Olivia's Venn diagram of the pillars of HPC, what do we cover with DeepCam? We cover a lot, and actually I think we could probably highlight every single thing in this diagram, but we chose the ones that we think this one is particularly well suited to stress. And I added in a software functionality bubble here for distributed PyTorch, because, for various reasons I won't get into in this talk, we have struggled scaling it given the flavor of network and hardware that we have at our institution. It's fine now, but the journey to get that was a little untenable for our current system. Next slide, please. And so just to briefly go over some of our requirements for DeepCam, we very much took some inspiration from NERSC, who I just feel like I can't credit enough to the development of this benchmark and some thoughts around it. We took some inspiration from them, but changed a few things up. So the way we approach this is basically by having a few different categories of submission types that people can use. So we have baseline and ported categories whose purpose is basically to enable that apples to apples comparison Olivia was talking about. Your goal is to basically fork the DeepCam implementation and not modify it at all and just run it with a set of hyperparameters we give the vendors and see how that looks. If you submit a ported category, you're allowed to change things to target other devices that might not be available in today's market, or maybe the code is just written in a way that can't use that hardware. You choose one of the two to submit, and then in addition to that, you can submit an optimized run where you can modify the training code to really showcase your hardware capabilities. We have a set of what we call mutable hyperparameters that vendors can change, such as the learning rate, and they can really tune this thing to their system to show us what it can really do. Next slide, please. And I'd be remiss to not show some data as a data nerd myself. This is just sort of what it looks like on our current system, running this unoptimized baseline sort of out of the box from the repository. And what I wanted to say here too is that on our end, as we evaluate results, we have a whole kind of toolbox of things that we use to profile these benchmarks and try to really understand what they're doing, what they're exercising on our current hardware, so we can be a little bit more prepared for responses we get later in 2026. So this is showing one of our in-house tools that can show some GPU device utilization and power draw, which as an energy lab, we are very interested in general. Next slide, please. Just to conclude, one more slide, sorry about that. I just wanted to conclude with a couple of overall impressions. I just wanted to say, from the perspective of DOE and procuring supercomputers in this ecosystem we work in, everyone is very on board with MLPerf. We have had many disagreements over the course of developing this set, but none of them have come from whether or not we use MLPerf. It's more, how do we choose which benchmark and what those run requirements should be? Hardware vendors have expressed in no uncertain terms that they are very happy our AI/ML benchmark comes from the ML Commons framework, and it's been used in at least one previous procurement, such as the one for NERSC here not too long ago. Our scientific and other stakeholders at the lab are very pleased that we thought hard about choosing a benchmark that represents a major category of their work, and we didn't just sort of choose something willy-nilly based on general industry trends, which we sort of buck against the grain a bit, at least at NREL. And to end on a selfish note, Olivia and I are very pleased that after all of this, we did not have to sit down and develop a segmentation model from scratch to use as a benchmark. This is already out there, already established. There's a paper on it. It won a very wonderful prize. That's excellent. So with that, one more slide, please, just as a thank you. Thank you very much for your time. We were thrilled to be invited and speak here. I'm sorry we couldn't make it out in person, but we would love to answer any questions you might have from email. So please do reach out to us anytime to connect, and Olivia and I would be happy to talk with you. Thank you, everyone.